Okay, so in the last section we talked about we talked a little bit about relativistic kinematics and Lorentz transformations, and also a bit about relativistic dynamics, the fact that the laws of nature have to be covariant, they have to be look the same to all inertial observers. And then in particular we mentioned the energy and momentum conservation, which is not the conservation of the sum of the four momenta between the initial state and final state. And then we talked about the concept of force. We defined it in analogy with the classical mechanics. And then we showed that that definition reduces to the usual Newtonian definition when we go to the rest frame. Why do we do that? Because in the rest frame, or when the velocities are small, we expect that the classical mechanics should be recovered. The non-relativistic mechanics should be recovered. So in the last lecture, we talked about force, F mu. But we also mentioned that we define for acceleration by just dividing the force by m, the rest mass, and that is the second derivative of x mu with respect to the proper time. So this is a valid for vector because dx mu d tau, we can also write this as d by d tau of u mu. So we say that u mu is a valid for vector and tau is proper time element is valid scalar, so we can take this derivative and define another for vector which we call for acceleration by the same argument that for force in the rest frame becomes the Newtonian force. This for acceleration in the rest frame becomes the Newtonian acceleration in the classical mechanics, namely the second derivative of the position, or first derivative of the velocity with respect to time in that frame. So in the rest frame, AI is a Newtonian, and then A0, we mentioned that it's 0 in the rest frame. Let me just briefly show how we can get this. We know that the for velocity u mu has a unit norm, or norm equals -1, basically by definition. So if I take the derivative of this, both sides of this equation with respect to tau, if I take the derivative of this equation with respect to tau, on the right hand side I get 0, and then on the left hand side I get twice u mu d u mu by d tau equal to 0. So the u mu by d tau is what we call the for acceleration. So this tells me that u mu times a mu is equal to 0. But in the rest frame, the rest frame velocity is instantaneously 0. Therefore, u mu is just 1, 0. Therefore, this expression is telling us that A0 in the rest frame is equal to 0. Any questions so far? Is it clear? Okay. Now, what is proper acceleration? Proper acceleration is the norm of this for acceleration. So let's call it alpha. Is the square root of a mu. Now this is a scalar quantity, right? So we can evaluate it in any frame that we like. In particular, we can evaluate it in the instantaneous rest frame. And there, since the zeroth component of the for acceleration is 0, this just reduces to the square root of the norm of Newtonian velocity. Sorry, Newtonian acceleration.
Actually, I'm used to the other signature.
Oh yeah, I'm using mostly plus signature.
Yeah.
So is this clear? So that's what I mean by proper acceleration, which is also the acceleration in the rest frame. Now we want to consider an observer who moves with constant proper acceleration in 1 + 1 dimension, one space and one time dimension. And we assume that that observer, we call him Bob, he starts at rest at the origin, and then he accelerates towards the positive x-axis with constant alpha. So if we want to draw the word line of this observer, qualitatively it's gonna look like this, right? Originally he's at rest, and with time his velocity is growing because he's accelerating. We can also understand that there has to be an asymptotic, right? Because we are talking about an observer who is a time-like observer. So what did we learn here? We learned here that or in the previous section, that the forward velocity of a time-like observer is fixed and is equal to has a norm which is equal to -1, right? So the tangent to this curve, which is the word line of this observer, so we can consider the tangent to this curve, and that is what we call the forward velocity. This tangent always has the norm equal to -1. Now, that implies that this trajectory can never become, can never have the slope exactly equal to 45 degrees, because that would be a null line which has norm equal to 0. So if someone is accelerating, the maximum velocity that they can have is the speed of light, and that can be reached only asymptotically. So therefore there will be the question now is that the qualitative feature of this curve is that the velocity is increasing, but it cannot increase past the speed of light. And what we are going to see is that there will be some last null ray that to which this trajectory is going to asymptote in the limit of infinite time. And the goal of the problem is to determine this time. The time at which this null ray, this last null ray that reaches the accelerating observer is going to intersect with x equal to 0 line. So we imagine there is an observer who lives, there is Bob who is accelerating, and then there is Alice who is at the origin, and then she's sending the messages to Bob who is escaping. Okay, so the first thing to do is to determine what is this trajectory, right? We want to understand first what is the equation that describes this world line. In other words, we want to know what is x of t, for instance. Or we can parameterize this curve in terms of the proper time of Bob, which means that in terms of the time that the onboard clock here is measuring. So that would be determining what is x of tau and what is t of tau. Once we have this x of tau and t of tau, then we can also determine what is x of t. Okay, so how do we determine this? First of all, we know that this Bob is a time-like observer, so I should have u mu equal to -1. Now, what is u mu? U mu is in this two-dimensional case, it is dt by d tau and dx by d tau. It's a two vector, and then this inner product becomes, and I use dots here just for brevity. So t dot and x dot. Dot means derivative with respect to the proper time. So then this equation becomes t dot squared minus x dot squared is equal to 1. Yes, except that we haven't, I mean, this equation is yes and no, actually, because this equation is more general. Any curve that you consider here for a time-like observer would satisfy this equation. This is not necessarily describing a hyperbole. This equation actually, it allows us to solve, for instance, t dot in terms of x dot. So if you give me the velocity as a function of the proper time, this, well, by velocity I mean, if you give me dx by d tau, then this equation tells me what should be dt by d tau. It also tells me that dx by d tau cannot, sorry, does it tell me? No, it doesn't tell me. So this tells me t dot is equal to the square root of 1 plus x dot squared. So far I haven't used the fact that this is an accelerating observer. I just used the fact that this is an observer, a physical observer, a time-like world line. Now we should use the fact that this is an accelerating observer. So what is the definition of having an accelerating observer? Our definition is that this object, this proper acceleration, has to be a constant. So we consider the proper acceleration, a mu, just take another derivative of this quantity, so it will be t double dot and x double dot. And the statement is that the norm of this 4 vector is fixed and is equal to alpha, which means that x double dot squared minus t double dot squared is equal to alpha squared. right? So now we use this equation. We know that T dot and X dot are not independent, they are related for any time like oscillator. So we can eliminate T from this equation to obtain a differential equation for X. So T dot is given by this, therefore T double dot will be, so we have X double dot square minus T double dot square. So what is T double dot? It is X double dot divided by square root of 1 plus X dot square, and then the whole thing is a square. So alpha squared. Therefore we have X double dot squared times 1 minus X dot squared over 1 plus X dot squared is equal to alpha squared. Therefore we have X double dot is equal to we have X double dot divided by the square root of 1 plus X dot squared is equal to alpha. And now we can solve this. So this is the differential equation for X dot as a function of tau. Remember, dots are derivatives with respect to tau, the proper. So we can integrate this differential equation to get that X dot is equal to sinh of alpha tau. There is an integration constant. The solution is sinh of alpha times tau minus some tau naught, some constant tau naught, but I choose the origin of the clock, the zero of the clock, to be at this point, at the starting point of the trajectory. At this point we start from zero velocity, therefore X dot at tau equal to 0 is equal to 0. So I fix the integration constant to be 0. So we have X dot, and then T dot is determined from here. It's given by cos alpha tau. And then from here we can integrate once more to get the trajectory. So the trajectory x of tau is equal to 1 over alpha times cos alpha tau minus 1. Again, I'm fixing the integration constant so that at tau equal to 0, bubble starts at the origin. So that's how I fix this one here. And then t is equal to sinh alpha tau. Now, this is indeed the equation of a hyperbola that is going through the origin. Any question up to here? Okay, so then we want to ask we want to imagine that we are sending signals here, or Alice is sending signals from the origin of this coordinates x equal to 0. She's sending signals. And for instance, we want to understand if a signal is sent at some time ta, which by the way is the same as tau a, because Alice is at rest, so her clock is measuring the same time as this t, as this coordinate time. So we want to see a signal that is sent at time ta, at what time or what point it arrives to Bob. Once we know that, then we can ask what is the time difference of two signals that are sent at time ta and ta plus some small delta ta. We can determine what is the time difference as measured by Bob. So it always useful to draw some pictures. So there is going to be one light signal that's sent here, and then it's arrived at that point. And then imagine there is a second one. So if we determine a signal that is sent at time ta, at what time it arrives to Bob, then we can also determine what is the frequency by which these frequent messages are observed. Okay, so how do we determine that? We have so what happens, so what is the description of this light signal? This is a 45-degree line that passes through the t-axis at t equals ta. So x is equal to t minus ta. That's the equation for this light signal that we are considering, or this text message that is sent, some electromagnetic wave. And we want to see when does it intersect the trajectory of Bob. So we want to plug in for the x and t these two values in here. So this tells me that cosh alpha tau, or 1 minus cosh alpha tau plus sinh alpha tau is equal to alpha ta. And therefore, so this difference is cosh alpha tau minus cosh alpha tau plus sinh alpha tau is this whole thing is 1 minus e to the minus alpha tau. So once again, we have alpha times ta is equal to 1 minus e to the minus alpha. So we already can see one thing. There will be a last signal. Well, we could also see it from here. It's a hyperbola, so it has an asymptote. Or we can see it from here. There will be a last signal. The last signal is going to arrive to Bob at tau equals infinity. So if I send tau to infinity here, I will obtain the time at which the last signal is sent. So that tells me t last is equal to 1 over alpha. And what else? We can also determine the frequency, right? We can ask if we have two signals with one of them as TA and one of them as TA plus BTA, then we can ask what is we call it delta TA. We can ask what is delta tau, which is, we should remember is tau of Bob, so it's really the time that Bob's clock is measuring. So this we can also determine from here. It's this equation just tells us that alpha times delta TA is equal to alpha delta tau times e to the minus alpha tau. So 1 over delta TA is the frequency of messages as sent by Alice. So this is 1 over omega A, and 1 over delta tau is the frequency at which the messages are arrived. So that is 1 over omega B e to the minus alpha. So omega B is equal to omega A e to the minus alpha tau, which means that if Alice is sending messages with constant frequency, the frequency by which they are arrived at Bob is going to go to 0. This is called redshift. Because the frequency goes down, red is below blue. Any questions? Yes.
What would Bob see after this time? After this?
There is no after this time because this is already happening at infinity. So remember, this T last is the latest time at which the signal was sent by Alice. That last signal will arrive to Bob when asymptotically, when his clock is going to infinity. So for Bob, there is no after this time.
So you will see everything black behind him. Like, there is no light reaching.
Well, so imagine you're Bob. What is the experience of Bob? As he accelerates, he keeps receiving messages, but these messages are going to arrive later and later at longer and longer intervals. Moreover, if these are some light signals with some frequency, the frequency of those light signals is going down. So imagine, for instance, he has a detector that measures in some range of frequencies, say visible light, and then Alice is sending signals which is in that frequency of the blue. As he moves away, then the frequency of the signals that are arriving to Bob, they go down, right? And they continuously go down to 0, so eventually they go outside of the band of his detector, and at that point he starts receiving things. But if he had a detector which would be sensitive to infinitely long wavelengths signals or infinitely low frequencies, he would continue receiving signals up to infinity, except that they would arrive at a longer and after longer and longer periods. Of course, this is a bit unphysical. This is something, an artifact of classical physics. Once you think about it in quantum mechanics, then there will be a time at which beyond that you would not be able to detect this signal because the frequency becomes extremely low, so you need, and you have a detector that has a size, that means that you have some lower bound on the wavelength, on the frequency of the signal that you can detect with that detector. So in reality, if you think about it in a real experiments and include quantum mechanics, then there will be a time at beyond which you don't see anything. But that depends on the properties of your detector. It's not it's not something that we can solve here.
So if Alice is sending a continuous signal, let's say that it's projecting a movie. So the movie is not just slowing down, but the picture is going red. Also.
Yeah.
But the movie will never end.
Well, it depends. I mean, if it's really a movie that you are watching, yeah, it becomes red. If it is the information that translates into a movie, then then I guess the color wouldn't change, but it will become slow. Okay, so there is another way to do this, maybe a little bit more formal, but it would be useful because maybe in some other setups it's easier to generalize. So instead of talking about messages that are being sent at different times and seeing at what time they arrive, we can also ask basically the equivalent question, which is imagine there is a photon that has a particular frequency as measured by Alice, and ask what is the frequency of that same photon when it arrives to Bob. We should get the same answer, right? Alice can set her clock according to the frequency of that photon, and then the answer we get for Bob has to be the same as the answer we get here. But we can also, this allows us to understand how photons translate, or how the frequency of a photon can be talked about, discussed in this formalism. So when I talk about a photon, what I have in mind is a particle with a 4 momentum or 2 momentum in this case, which is null. And since it is null and we are in 2 dimensions, it should be of this form if it is right moving. And then when I talk about the frequency of the photon, so this omega is the frequency of the photon. Of course, the frequency of the photon is an observer-dependent thing. So this is the frequency of the photon in this particular frame that I consider. What frame is it? This is the rest frame of Alice. So in this frame, the forward velocity of Alice is just 1, 0. Maybe I should write this also as a column. And then the frequency of the photon in this frame, which is the same thing as the frequency of the photon measured by Alice, is this omega is nothing but minus UA dot K, which is minus UA mu K mu. Right? So what I have done here is that I have written a Lorentz invariant expression for the frequency of the photon measured by Alice. So omega A is equal to minus UA dot K. Obviously, it has to be a Lorentz invariant object, a Lorentz scale, because when I refer to frequency as measured by someone, that should be agreed upon by all observers. Everyone agrees that someone, what should be the frequency that someone measures for the photon. That's just a number. And this is also true. And this will be correct for any observer. For any observer, omega, the frequency of the photon would be given by minus velocity, for velocity of that observer, dot, the Lorentz product of that with k mu. So similarly for Bob, that is true. Now here we have the velocity of Bob. So in order to understand what is the frequency of the signal as measured by Bob, all that we need to do is to remember that the two velocity of Bob is given by right over there. So it is sinh alpha tau and cos alpha tau. Therefore, omega b is equal to. So since so we agreed that omega a is just the first component of this. Let me just call this omega a here. We are measuring this in the rest frame of Alice. And omega b is equal to minus dot product of these two vector and these two vector. So that gives me omega a times sinh.
Because you put this correctly.
This is better. Which is omega a times e to the minus alpha tau, which is the same. Any question? Okay, then let me say a few words about the next subject. So now I'm going to completely change the subject. Maybe not completely. I'm going to talk about the variation principle and review a couple of examples, and then in the next lecture we can talk about the nodal theorem.
I think that you explained like another type of this problem, right? That you have like Alice and Bob, that they are both oscillating, right?
Yes, yeah.
What would be the difference in the final result? Be similar to this?
It's similar, but it's I mean the calculations is similar, but the real final answer is different in the sense that there is no you will find a fixed here, if you see that the redshift is going to infinity, in the sense that omega p is going to 0, which is this fact that eventually you don't, the messages are going to arrive later and later. So this is not going to be the case in that example. You will get a constant redshift because both of the observers are accelerating. But the way to solve it is very similar to how we solve this problem. In fact, you can probably find a clever way of exactly mapping it to this problem.
You're accelerating in the same direction, right?
Yes, but they have different proper acceleration. So in modern physics, we have learned that it's very useful to use variation principle to identify the dynamical degrees of freedom that are relevant for the description of the system we are interested in, and then write an action for those dynamical degrees of freedom. And in many circumstances, this works very nice. We write just the general action, the most general action for those dynamical variables, and that most general action gives us the equations that are describing the evolution of the system, up to some certain parameters that we have to determine experimentally. So for instance, we can think of the standard model of particle physics, something that we can build based on this principle. Identify what are the degrees of freedom and then write the action for this, the most general action for these degrees of freedom that we so now what we want to do is to here consider some simple examples of how we write the action and do variation principle, and then some small checks that they reproduce what we knew from classical physics. So here there will be a set of examples. So the simplest example is just consider the action for a scalar field, free scalar field in 4 dimensions. So this is given by -1/2 d phi squared minus 1/2 n squared phi squared. Have you seen this action before in other courses? So this is perhaps one of the easiest examples. What does this action give us? For instance, it gives us the Klein-Gordon equation, the equation of motion for this free massive scalar field. And the way it gives us that is that we take the variation of the action and we require that to be stationary under those variations. So we want to send phi to phi plus some delta phi, where delta phi is some arbitrary localized variation, and require that delta of s, the linearized variation of the action under this change, is equal to 0. So if we do this substitution in here, what we get for delta s is equal to integral d4x d mu minus d mu delta phi d mu phi minus m squared delta phi times phi. And this we can write it as integral d4x times delta phi times box phi minus m squared phi minus d mu minus the total derivative d mu of delta phi d mu phi. Of course, the whole thing is inside the integral. Now, since we took this delta phi to be a localized variation, meaning that delta phi is 0 as I go to the boundaries of my space-time region, this total derivative term is irrelevant because I can reduce it to a boundary term, and at boundaries delta phi vanishes. And therefore, for the variation to be 0 for arbitrary localized delta phi, this expression has to be 0, which gives us the Klein-Gordon equation. So this is example number 1. Klein-Gordon. Any questions about the scalar field? No. Well, in the case of electromagnetism, in the case of the Maxwell theory, we can similarly derive Maxwell's equations in terms of from variation of an action, which is written for the potential for the 4 potential A mu. So electromagnetic fields, the Maxwell theory was originally formulated in terms of electric and magnetic field. We can put them together inside F mu nu, inside the 4 tensor, anti-symmetric 4 tensor, called F mu nu. So then F0I is the electric field and Fij is the magnetic field. And this anti-symmetric tensor, by one of the Maxwell's equation, this has 0 curl, which means that it can be written as exterior derivative of a potential, anti-symmetric derivative of a potential. So that the anti-symmetric derivative of F mu nu is equal to 0. And you can write an action for A mu such that the variation of this action with respect to A mu gives us the Maxwell equation. So how does it look like, this action? Again, I'm sure you have seen it before. It is minus 1/4 F mu nu squared plus A mu J mu, where J mu is a current, electromagnetic current. And again, we follow the same rule. If we vary the action, if we change A mu by some arbitrary localized variation, we want delta S to be 0. This delta S is given by d4x delta A mu times d mu of f nu mu plus j mu minus a boundary term that is again irrelevant because the variation is chosen to vanish at infinity. And therefore require that the variation of the action is equal to 0 for arbitrary localized delta A. It gives us the Maxwell equation d nu if nu mu is equal to minus j mu. Any question so far? Okay, the third example is the point particle action. This is particularly useful for our course. Because why? Because this point particle action is an action that we write for a particle that lives on some background field, moves on some background field. Depending on what background field we have, we modify this point particle action to incorporate the coupling of this particle to the background field. And the variation of this action should give us the equation of motion for that particle. So for instance, if we have a charged particle, so again, this is on a space-time. This is a space-time diagram. If you have a charged particle that moves in the presence of some background electromagnetic field, so what does it mean? Here we have some non-zero a mu field, and there is a particle with charge and moves in here. So it has some charge and some mass. The trajectory of this particle is described by some x and t of as functions of, for instance, its proper time or any other parameter. So we have a set of x's. Let's call them x mu. So I use capital X to describe the position of the particle. So this x mu is parameterized by something. Let's call it sigma. Sigma is the parameter of the curve. So for instance, you can imagine that this particle starts its life when sigma is equal to 0. So at point x mu of 0, and then when sigma is 1, it arrives to the final point, x mu of 1. So this x mu of 0 is x initial, and then x mu of 1 is equal to x final.
So you can also use the proper time.
You can also use the proper time. Yeah. I'm not using the proper time to emphasize that you could use anything. But of course the proper time is convenient for many purposes. Okay, so now if we want to write we want to find an equation of motion for x mu to find how this particle moves in this background field. And the rules for constructing the action is to write all objects that are allowed by symmetries. And then the organizing principle, normally there are infinitely many objects that are allowed by symmetries. The organizing principle would be derivative expansion. So we want to have minimum number of derivatives inside the action. Why? Because at larger times and larger distances, the terms with lowest number of derivatives are the most relevant ones. This you will see probably more in the future, these examples of this organizing principle. But so here, for instance, what can we construct? One object that we can construct for this trajectory, for this word line, is the proper length. So if I want to measure the proper, and then we should multiply by something that with some a posteriori knowledge, I want to call it m, and I want to here write the length of the curve that is parameterized like this. So that length is what we have been talking about in the previous lecture. You can divide it into infinitesimal elements and add them up along this as we sum using this parameter sigma. So what do we get? We get an integral over sigma minus eta mu nu, and we have minus because this is a time-like curve, and I choose a mostly plus signature for the metric. So I will have this dx mu d sigma, dx mu d sigma. So this gives me the proper length of the curve. This is clearly something that is invariant under symmetries. In any Lorentz frame that we go, this expression is universal, meaning that it gives us it's the same object. Or something that I didn't say, action should be, of course, invariant under Lorentz symmetry. So we should obtain a scalar quantity. And then it's a charged particle, so you should couple to this mu field. Mu field is a 4 vector. Therefore, in order to couple it to the word line, we have to use an intrinsic 4 vector of the word line, which again with some a posteriori knowledge, I choose it to be the tangent vector, dx mu d sigma times a mu.
You can also see it by the fact that if you multiply charge by force velocity, it corresponds to current.
If I multiply the charge by for velocity, it corresponds to the current. Yes. In fact, that is exactly a consistency check of this choice. Yes. If we add this action to the original action that we had, and then derive what source we get for the Maxwell equation, we get the source that is what we would expect from a charged particle moving on a fixed trajectory. Okay, so now if we have this action, we can again do the variation of the action to derive an equation of motion for it. So we follow again the same rules. X mu goes to x mu plus delta x mu. And delta x mu is arbitrary but localized. Localized here means that it vanishes at the boundaries of this interval. So we don't change the boundary values. And so then the variation of this action is going to be given by m integral d sigma minus eta mu d delta x mu d sigma dx mu d sigma. Okay, so this is what I get from the first term, and then from the second term there will be two contributions. One is coming from the variation of this x mu. And then the other one comes from the fact that this A mu itself is evaluated at the position of the particle. So this is A mu at the position along this word line. So the argument of A mu depends on x mu. So that gives me an additional term d mu A mu times delta x mu. Now we can do some integration by parts and discard the boundary terms. So here what we get is there will be an integral d sigma, there is delta x mu, and then from here what I get is m times d by d sigma of eta mu nu dx nu d sigma divided by this square root. I don't write it anymore. This is its square. Here I get minus q times d a mu d sigma minus d mu a mu no d mu a mu dx mu by d sigma. And then the boundary terms I don't write anymore. There will be terms which are just total derivatives with respect to sigma that I throw away. Okay, so now what do we do with this derivative of a mu? So first of all, this is basically our equation of motion, because that's the part that multiplies delta x mu. Delta x mu is arbitrary, therefore what multiplies it has to be 0. So that is the equation of motion. Now we can simplify it a bit. So first simplification is that d a mu by d sigma can be related to the velocity, because the way a mu depends on sigma is implicit, is through its dependence on x. So this a mu, you remember, is a function of x, which is itself a function of sigma. Therefore, d a mu d sigma is d mu a mu times dx mu d sigma. Another thing that we can do is to now express our equations, which was written for this parameter sigma. We can express it in terms of the proper time. So what is the relation between the proper time, or derivative with respect to proper time and derivative with respect to sigma? That's from the definition of the proper time. This is nothing but this is square root that we had there. So if we use that, then that equation becomes m times d by d tau of eta mu nu dx nu d tau is equal to q times f mu nu times dx nu by d tau. Actually, mine. Of course, eta mu nu is constant, so I can take it out. So I have, and then I can multiply everything by inverse of eta mu nu. So I get the second derivative of x mu with respect to tau is equal to minus q times f mu nu times u nu, where u nu is a forward velocity. And this equation, which is supposed to describe the motion of a particle in an electromagnetic field, that is, we can go and check what is its non-relativistic limit and verify that this is indeed the Lorentz force. Gives a Newton's second law with the force which is the Lorentz force. Okay, I guess I'll stop here.